I'm not going to do all of the questions in this example problem, but I'll work through some of them, arm you with enough of the principles to be able to tackle the rest on your own, okay? So when naming ionic compounds, that is compounds made of one or more metals bonded to one or more nonmetals, as I've outlined in an earlier video linked to in the description below and hopefully floating over my head somewhere. You start by focusing on the first half of the name, which is the name of the metal. In this case, I've had potassium. Potassium is on the periodic table in column 1. Its atomic formula is K. The second half of the name is the name of the nonmetal or nonmetal polyatomic anion, or whatever we have here. This is sulfide. What is sulfide? Well, sulfide happens to be a sulfur, which is located to the right region of the periodic table, that has a -2 charge. So it helps, by the way, as we're doing this, to write down the charges above them. Now you'll note again, because potassium is in column 1 of the periodic table, it will always have a +1 charge whenever it's found in a compound, okay? Whereas sulfide is 2 columns away from the nearest noble gas, therefore it always wants a -2 charge in order to feel like a noble gas. Remember by the octet rule that losing electrons shifts an element one box to the left for each positive charge it has, or electron loss in terms of how it feels electrically, and gaining an electron moves a box or an element 1 box to the right on the periodic table in terms of how it feels electrically. Hopefully that makes sense, okay? So again, because I've got potassium being a +1 charge and sulfide being a -1 or -2 charge here, I can write those up here. What do we have to do in order to make those, put those atoms together to have them cancel out each other's charges? Well, what I'm going to have to do, and this is a good kind of tip to use, is you can go up here and grab the charge here and bring it down and have it be the subscript for the element on the left, and then you can take the charge here and bring it down here and have it be the subscript for the element on the right. You see, if I have 2 potassiums, which is what that implies, each one has a +1 charge, then the total charge ebbing off of them combined is 2 times +1, which is +2. That will cancel out the -2 charge coming off of the 1 sulfur. Typically, we don't leave 1s as subscripts, and we don't leave the charges floating up them or above them when we write down our final formula. So that is the formula for potassium sulfide, okay? Now what about nickel 2 perchlorate? Let's start with the leftmost name, nickel. Okay, that is a nickel. Now nickel is not found in columns 1 or 2 of the periodic table. It's in the D block. D block metals often have the ability to exist in multiple different charges or oxidation states. And that's why when you're naming a compound as a D block metal, you have to put in parentheses in Roman numerals the charge for that D block metal in that specific compound, okay? So this is nickel 2 perchlorate as opposed to nickel 4 or nickel 3 perchlorate or something like that that would have a completely different formula, okay? But the beauty of that is that it tells you in the formula what the charge of the nickel is, so you don't have to figure it out by looking at the periodic table. You just write down +2 floating over the nickel for bookkeeping purposes. Now what about perchlorate? What is that? Well, perchlorate is a polyatomic anion that has a complicated formula of ClO4, and as a whole, it has a charge of -1. So I'm just writing a -1 above that. Now, I do not require my university students to memorize perchlorate. I do require them to memorize a bunch of other polyatomic anions and 1 cation ammonium that's shown right here. Nevertheless, you can look up perchlorate on the internet or something if you want. How do I do this? Well, in order to make these charges balance, again, what I'm going to do is I'm going to use the charge up here and bring it down here as a subscript for the anion, the thing on the right, and I'll bring the charge up here, get rid of the sign, and bring it down here as a subscript for the cation on the left. Okay, so our formula is starting to take shape. Whenever we have a 1 here as a subscript, we just erase it because whenever you don't have a subscript, it's an implied or understood 1. Now here's the problem with polyatomics. You can't just leave a floating subscript of -2 sitting there when you're talking about an entire polyatomic, that is, an ion that has more than 1 atom. You can't just leave a 2 floating there. Because what does that mean? Does it mean that I'm just talking about 2 oxygens or 2 times 4 oxygens? What am I talking about? Well, in order to make that a little bit clearer, what we're going to do is we wrap parentheses around the entire thing and then leave the 2 down there outside the parentheses so that it tells the reader that we have 2 total perchlorate anions in this formula, each of which, as we know, has a -1 charge, and they are bound together with a nickel that, according to this name, has a +2 charge. +2 canceling out the -2 total, ebbing off of the 2 individually -1 charged perchlorates. Does that make sense? Good. Now let's take a look here. Potassium sulfate. Potassium, again, is in column 1 of the periodic table, so it has a +1 charge. We'll write that for bookkeeping purposes floating up there. Sulfate is one of the polyatomic anions I do require my students to memorize. It has a formula of SO4 and a total charge ebbing off of the entire thing of -2. We'll do the crosswise technique, I guess, here. I bring the 2 down here. That will be my subscript for the potassium. And I bring the 1 down here. and that would be the subscript for the sulfate. Now again, 1s, we don't have to worry about leaving them because anytime you don't see a subscript, it's an implied one. So I can just erase that there, implying that we just have 1 sulfate attached to 2 potassiums. And if you do the math, you can see that the total charge ebbing off of the potassium should cancel out the negative 2 charge ebbing off of the sulfate. That is the formula for potassium sulfate. Here we have aluminum hydroxide. Now aluminum has a formula of Al, and it is not located in the D block. As it turns out, anytime you have aluminum in a compound, it will always have a +3 charge as shown on this chart, okay? So I'm going to make note of that, +3 over the aluminum. What is hydroxide? Well, that is a polyatomic. I do require my students to memorize. It has a formula of OH and a total charge of it of -1, okay? So how do I make those balance? Well, again, I'm going to grab that 1, I'm going to bring it down as the subscript for the aluminum. I'm going to grab that 3, bring it down as the subscript for the hydroxide. However, because hydroxide is a polyatomic, that is an ion that has more than 1 atom, I can't just leave the 3 floating there next to the H, because that might tell the reader that I just have 3 H's and only 1 O, and that's not what we're talking about. We're saying that we have 3 total hydroxide OH's, or OH units as a whole. So in order to make this all make sense, I have to wrap parentheses around the hydroxide, and of course, as we did before, we can erase the 1 because it's implied. So the formula for aluminum hydroxide is that right there. So there you're armed with some methods on how to do some of these. I'll let you tackle the rest on your own.